Hello folks, and welcome to a repair follow-along video. Today I'm going to be working on a repair of this Takahashi Sky Patrol II. The Takahashi Sky Patrol II is a motorized mount for a telescope. This one's supposed to work so that it will generally track along if you leave it alone, but you also can pause it or you can speed it up to kind of fine-tune adjust the position. However, in this particular case, it's not moving at all. So let's dig into it and see if we can repair it. So the first thing that I'll do when I'm working on a board that doesn't have schematics is I will try to reverse engineer the boards, come up with a circuit diagram, and that way we can identify what should be where, and we can start taking measurements to see what's not correct. The Takahashi Sky Patrol II consists of two major boards. This one here that's connected to the motors is the power board, and then it's connected via one of these little connectors, kind of a mini DIN style connector, to the main board, which is in the remote, which has the buttons to advance or hold, and then a directional switch as well, and the overall power switch. So what I'll typically do for this is I'll take high-resolution photos of both the top and bottom of the board, put them on separate layers, adjust them using the unified transform tool. So you could take something, you can actually go adjust it like this. You can take it, you can skew it, and all of that allows you to kind of align the top and bottom of the boards so you can start tracing connections. Then you can take the layers, and as you're tracing connections through, you can adjust the opacity of the top and bottom layers so that you can see where they connect. So for example, right here on the bottom of the board, we can see this trace through here, and it connects through to this top layer trace that is mentioned as pin 5 through that via there. This works pretty well for 2-layer boards. Sometimes with 4-layer boards you can guess at it, but it's a great place to start, especially for simple designs like this. So I went through and reverse engineered the schematic for the power board here, and then for the main board here as well. Same general idea. You have the 2 layers, and you could trace them through and figure out where everything is connected by just adjusting the opacity, identifying net names, and then placing everything down. In reviewing the connections, I was able to identify that the stepper motors are set up in a unipolar connection with these middle taps tied together. And then you have separate white and blue, black and yellow taps for the A and B coils. And we can identify the impedances, expected impedances, using just a simple multimeter if we have it disconnected, or if we have the motor out of the circuit, we can get this type of testing here. So that allows us to identify the overall circuit for the motor connection and confirm that at least the motor impedances are fine. So it's likely not an issue with the motor, or at least it isn't yet. This is the schematic capture for that power board. And the main things we can learn from this are the power supply, which is 5 volts. We can determine that by looking at the rated supply voltages for the chips on the main board, which is shared. And we can also identify that the barrel jack that is used for power on here is a positive center tap. So that is useful to know the polarity of that connector. And then we have our stepper motor wires here, red being that center tap on each of the coils for unipolar connection. And then we have the white, blue, yellow, black phases. And this is the schematic capture for the main remote board. We'll kind of walk through this bit by bit. I kind of break it up and have named nets. It's just an easy way to figure these things out. So this is the mini DIN connector that comes from the main power board. We see we have our 5-volt rail. There's a diode that prevents us from reverse biasing it, so our VDD rail is approximately 5 volts. And then we have our coil connections here. Those will ultimately go to our stepper motor controller. Then we have a switch here. This is a switch that has a built-in LED, so that's why you see this extra functionality, but otherwise it's a pretty simple, straightforward switching capability, where the switched ground is connected to the ground if it's connected and switched on. Then we have our clock for the circuit. This is a custom part that is a 374.214 kilohertz Meta CMOS oscillator. So this outputs CMOS level signals, but it has an internal crystal. And we have, again, that switch ground, we have VDD, and then we have a clock output here. Then next up, we have this 14-bit asynchronous binary counter chip. It's a standard SN74HC series binary counter chip. We have our clock input comes in here, and then effectively each of these outputs a division by 2 of that clock. So this clock is divided down ultimately to the rate that we actually want to pulse things at. And the notable thing here is we have this clock step output here, and depending on which of these push buttons are pushed, we can either stop it. So if we push this push button, then the clock step is pulled to ground and no clock is provided to the rest of the circuit. So we do not step or advance the circuit. And in this case, we have our two dividers here, M and N being the more divided item. And so by default, it moves very slowly on this N divider. And if we push this switch here, then that allows us to connect it to instead the M, which will move twice as fast. So this is if we need to, for example, quickly catch up. You can push that button to advance a little bit faster than the default clocking rate. And lastly, we have this Toshiba TA8415P unipolar stepper motor driver. It's a nice, neat little chip that allows for pretty simple control of a stepper motor. In this case, notably, we have this clock 2 pin that is pulled high. So if we look at the truth table, whenever clock 2 pin is pulled high, then when the clockwise counterclockwise pin is low, then we go clockwise, and when it's high, we go counterclockwise. So if we go back to the actual circuit that is set up in this case, the enable pin, this is high as long as the output is enabled, so when the thing is turned on, and the counterclockwise pin is what I named it here, but this pin effectively is pulled high, pulled up to this enable whenever the little tiny directional switch is disconnected. Otherwise, that pin can be shorted to ground, and then this counterclockwise pin is pulled low. So that allows you to change the direction from clockwise to counterclockwise. Then we have our clock step that comes in here from the rest of the circuit. To decide what the actual driver will do with that clock step, we then need to look at this EA, EB, and 3-4 pins. 3-4 is tied low, EA is tied low, and EB is tied high. So if we look at the data sheet for the driver, we'll see that under that circumstances we're in a 4-phase mode and we have 1-2 phase excitation. So now that we have a good understanding of how the circuit is supposed to work, we can get down to debugging. The first thing to check, obviously, is that power and ground are working properly. So if we take this, plug it in, turn it on, turn on this switch here, we can then confirm that ground is indeed pulled low, and the 5 volts rail is indeed at 5 volts, pretty close. It's a little bit droopy because of the diode here, but that's expected. That's well within the tolerances of these chips. Next thing we can do is check to see if the oscillator is putting out the correct frequency. In this particular case, since it is a simple CMOS standalone oscillator, we should be able to probe the output clock and confirm that it's at or near this 374.214 kilohertz frequency. It was at this moment during troubleshooting that I realized that this is at least one of the bad parts. When I probe the output of this, it starts out near 0, slowly rises up to near 5 volts, and then just stays there. No clock output whatsoever. And of course, no clock output means no pulses going to the driver, and ultimately no stepper motor stepping. So to confirm that that was the issue, I started out by desoldering this crystal oscillator, pulled it out of the circuit, and tried it out on a breadboard. No luck, it produced the exact same response. Then, to see if the rest of the circuit worked with this oscillator repaired, I hooked up an arbitrary waveform generator and generated a 374.214 kilohertz square wave and put it in on pin 5. As soon as I did that, the rest of the circuit came to life. The stepper motor started stepping. I was able to advance it, slow it down, or pause it at will. And so this confirms that this one chip, this crystal oscillator, is indeed the faulty component. At this point, we're in a bit of a conundrum. While we are able to find a datasheet for this part, it's from a company called Mita Denpa in Japan, it appears to be a custom manufactured frequency. In particular, Even with searching all over, I was unable to find any other manufacturer that made a crystal of that particular frequency, let alone one in that package or with that voltage level. There were a couple of places that did custom crystal manufacturing. However, they had a minimum order size of 1,000 units, which is completely unusable for a single unit repair like this one. So I took a different approach. This company, SI Time, manufactures custom MEMS-based oscillators. And in particular, they have one series that allows for a wide range of programmable frequencies that are factory programmed and incredibly good stability, at least as good as the crystal oscillator that we'll be replacing. The one complication that I found is that I could not find a MEMS oscillator that operates on a 5-volt supply voltage. However, that is something that we can reasonably fix with just a few extra chips. And that's where I came up with this design for a custom replacement board. It fits in the same footprint. However, in this case, it takes the 5 volts in and steps it down to 3.3 volts for the crystal oscillator. The clock output is then level translated back up to 5 volts for the output. The PCB design is pretty straightforward. Our 5 volt input pin goes to this LDO to generate 3.3 volts for our oscillator. The oscillator chip generates the clock signal, which is then level translated and then sent out the normal clock pin here. Once the board arrived, it was time to solder it up. The first thing I'm doing here is using a solder stencil to apply exactly the right amount of solder to the pads. It's not strictly necessary, but for a board with pads this small, it can be very helpful to help you get exactly the right amount of solder on each of the pads. After that, it's time to populate the board with the components and solder them all into place using hot air. I typically start with all of the passive components, the resistors and capacitors and such, and then I move on to the chips. For each of the chips, it's important to pay attention to the orientation of the chip before placing it down. For U1 here, I noticed that I had an issue in my solder mask design, and the center pad didn't get any solder on it, so I add a little dollop of solder. Alignment doesn't have to be perfect at this point because the solder surface tension will pull it into place, but it does need to be close. Once all the chips are on the board, it's time to solder them. We break out the hot air and slowly heat the board, as well as heat it from below with a preheater. Once the solder melts, all the chips will snap into place, and we can make gentle adjustments using our pair of tweezers. Once the surface mount components are soldered, we can then solder on the main header through-hole pins using a regular soldering iron. With the board finished, it's finally time to test it and see if it puts out the correct frequency. I hooked it up with a power supply and oscilloscope, and we were able to confirm that indeed it was generating a square wave of the desired frequency. So now, let's put it into the system and see if it works. We solder the new oscillator board into the remote board in place of the old crystal chip, and then give it a shot. And there it is! Full functionality has been restored. It can move in a counterclockwise direction. We can push the red button to make it go twice as fast. We can push the blue button to make it stop. We can change the direction back to clockwise, and it will move in that direction. And similarly, when moving clockwise, we can push the button to make it go twice as fast, or push the other button to make it stop. This concludes this repair video of the Takahashi Sky Patrol II. I hope you enjoyed. Like if you liked, and subscribe for more videos like this one.